This video will discuss the solution to question 9, which is a true-false statement that goes as follows. Figure 4 shows the Miller compensation. The pole frequency associated with node Vout will be at DC if Cm is extremely large, i.e. Cm is infinity. So to investigate this question, we need to look at the pole frequency at Vout. And the easiest way to do that is by looking at the time constant at that node. Now the time constant at any node is just the product of the equivalent resistance at that node and the equivalent capacitance at that node. Since we only look at the influence of the Miller capacitance, we can safely assume that the equivalent resistance is constant. So we're not going to look at that, but we will take a look at the definition of our equivalent capacitance, because that of course is changed by Cm. So to compute that equivalent capacitance, you need to take Cm and then apply the Miller effect, because we have it between two stages of an amplifier. So that is 1 plus 1 over A and not 1 plus A, for the reason that Vout in this case is the output of your amplifier. So that's where this inversion comes from. Now, since Cm is actually infinite or assumed infinite, C equivalent will also be infinite, and naturally the time constant will also be infinitely large. Now, to compute the pole frequency, we simply take the inverse of the time constant. And since that time constant is almost infinitely large, this pole frequency will actually go to 0 radians per second. And 0 radians per second is by definition the same as DC. So the statement above, saying that the pole frequency at Vout will be at DC, is indeed true.